Hey, hi, Mara.
Hello. Hello, Juan. Hello, everyone.
Hi. So on today's episode, we're gonna talk about a little bit over exploits and what are the new trends and what is happening in the wild. Also with Exploit Pack, we have a new website.
Yes, we
So,
do.
mhm,
Yeah, many things have improved.
mhm.
And yeah, I think it's smoother now, right?
Yeah,
Yeah, the whole process.
it should be smoother and faster, and the website load, and also our website is we had an adapted to the new trends. The website not only exploit trends but also
Yeah.
website trends. There are trends everywhere. So we changed the way that people has to interact with the website, how to find the products, the tools, and also. Something really cool for our customers is that we have so now you can create an account, and there we can share like the new exploits, new updates, and so on. So the whole process will be smoother.
Yes.
So
And
that's awesome.
another very cool thing for customers and also for non-customers is that now we have a blog
Yeah, indeed, true. Yeah,
news
yeah.
and with technical stuff.
Hmm.
And yes, well, all your research, all the research that you've been doing, it will be
Hmm.
there.
Yeah, yeah. And actually, there is already 4 blogs
Yeah.
that I uploaded there, and more are coming. But today's topic, going back to today's topic, is over exploit trends. As you might see online, I'm quite busy with exploit for kernel on
Yes, I've been
Windows.
seeing that.
Hmm. And just yesterday, I posted 5 new exploits using double R MSR. Um, so using the template that I made myself is basically a universal exploit that you can use against vulnerable drivers with an
Mhm.
exposed write MSR and read MSR. So if you have that in a vulnerable driver, then you have to find the IOCTL call and the code, and then you can use this exploit because it's universal, and then you can use it to actually get arbitrary code execution in the kernel
And
to the WR MSR.
and who is at risk of having these vulnerable drivers?
Well, so if you have these drivers installed in your computer, of course you are at risk because someone could take after. This is always for post exploitation, right? So
Yeah.
after they have access to your computer, they could use these drivers to disable AVs, to gain privileges, and also disable the other security protections that you may have. Like if it's an endpoint, they could disable, bypass, or interact as they wanted with the EDR or AVs. Those are security mechanisms that you will see typically in place on endpoints.
Mhm.
And of course, gain privileged access to the kernel, meaning ring zero access. That will lead to the highest privilege that you could have in a computer.
And is there a way to avoid being attacked by these vulnerable drivers and people who might abuse of this?
Yes, so you should have the latest at least. So I will start having the latest versions of the operating system that you have. Like for example, these WRMSR exploits, they will not work on Windows 11. So if you move to
Okay.
Windows 11 or the latest Windows 10, I think it was implemented on the latest Windows 10. But to be on the safe side, just get the latest Windows 11, install all the Windows updates, and then you will get some protections directly coming from Microsoft itself.
Good.
But there are other, of course, exploit classes, that's like the one that I'm gonna show you now. And
Mhm.
also, for example, I also posted a few other exploits for physical memory primitives. So basically, you read and write directly on the physical memory on the RAM itself,
Okay.
and that exploit class works on Windows 11. So they are not so they are protections, but in this case you can circumvent those protections. A good example would be On Windows 10, you could use, there are several ways. I'm just gonna name two. But in Windows 10, you could call NT-query system information to get the kernel base address or the address of a driver. Uh, and that has been disabled on the latest Windows 10 and on Windows 11. But because we are talking about post-exploitation, there are other ways to leak the base address. And if you have a medium integrity process that you should have because you are loading a driver or interacting with a driver, then you can call a new device that can be used to it's not leak because you are not doing a memory leak, then gathering the base address of the empty kernel. But what you are doing is just asking for it, just like with the empty query system information that you were doing. So this is another way. There are other ways as well of getting that, because in this particular case that I just mentioned, for physical memory access, you could use the vulnerability itself to get the base kernel address. Why do we want that? Because remember, we need to find the offsets when you want to interact with the kernel. The kernel itself runs with a kernel space layout randomization, meaning that the layout of the memory in the kernel will change. I can actually show you an example.
Yeah.
Yeah, if you want that. So here I'm on my Windows machine, on a Windows host, and then I have running on this Windows host, I have WinDBG, that is the Microsoft debugger. I'm using it to debug the kernel inside this virtual machine. And let me just show you an example. This is already connected to that machine. I'm connected to it using the network itself, the Ethernet. You could connect to this machine from this WinDBG, the debugger, to this machine, basically to the kernel itself of running on this virtual machine as target. This machine is running Windows 10, and you could connect to it in several ways using a pipe. Yeah, there are different ways, but the easiest way is the network. I made a bad script for that. So basically, you have to set this basic edit debug on to set the debugging on, and then you have to set basic edit debug settings, and then you set that you're gonna do it through net, as I said, through networking. The host IP, that is the host where it's running the Windows DBG, in this case, this machine. So that's the IP address, and then the port. The default port is 15,000. So that's the port I'm setting. So now it's already connected. I have rebooted this machine, so it is connected here. So you see, if I click on break, then I'm sending an entry. That's the opcode for interruption tree. That meaning that is the kernel is going to stop right there. And as you can see, my mouse is freeze. If I go out of the VM, because the whole machine has frozen, and if I click go or play, then the machine will start working again. There is something really handy with WinDBG. I don't know if you notice, but as soon as I click play, it gives me also as a memory the command that is running. So it's not that it's just sending the command, but it's also giving you the command on the prompt itself. So if you do anything using the icons, you will also get the command there. So now it's running. Let's load an exploit, a driver. So what I'm gonna do here, I'm gonna load a driver using IOCTL++. You can get IOCTL++ from exploitpack.com, but you have to be a customer of us. Then you can get the tool. So this tool allows you to load a driver. I'm gonna load this driver.
And how did you identify all those vulnerable drivers?
You can identify those vulnerable drivers by using IDA with the driver body reloaded, looking for interesting functions and so on. There are other, and there is also IOCTL Lance. That's a project that you can run to statically analyze the code of a driver. And you can also use Hydra. There is also a plugin for Hydra, similar to driver body reloaded, that you can use. Also, you can also use in Hydra if you don't have a license of IDA.
Of IDA.
There is also a really cool plugin that you can use either with IDA or with Hydra. I'm not going to show it today, but it's RedSync. It's basically a plugin that you can use to synchronize what you are doing with WinDBG with your static code analyzer, that it could be either IDA or Hydra. So that's for a different episode when we will talk a little bit more deeper. But I want to show you here, like I have this driver loaded using IOCTL++. So I selected the driver and then I load it. And then what I'm gonna do is to click on stop, on WinDBG. Now this machine is frozen, the kernel is frozen. And from here, what I can do is to list. I'm gonna list all the drivers using this command, lm dbm, and then the name of the driver. If I don't type the name of the driver, I can see the whole list instead of just that driver. So I'm gonna do it for only that one. But if I click, look, this is what I was saying about giving you the commands with WinDBG. That's quite useful. If I click on browse full module list, it's not only gonna do it, but also it's gonna give me the command. So if I click on it, I can also reuse that command, right? So that's quite useful. But now it has listed all the drivers. I don't want to list all the drivers. What I want to do is only get that particular one. And why I want to see it? Because now, remember I mentioned the kernel space layout randomization. So this is the base address of this driver. So if I want to set a breakpoint, I cannot just set a breakpoint on the driver because I don't know the address, and the address will change every time the machine reboots. It will change the layout of the memory. So it will not start on the same base address. So in this way, I have this WinDBG, this debugger connected to the kernel. Then I, using the debugger and using this command, I found the base address of this driver. And then using this base address, I can go into IDA. It will be the same for Hydra or any other debugger. It's the same process. I'm going to show it with IDA. So here in IDA, if I want to set a breakpoint somewhere, I need to know where. So what I need to do here is to link the base address that I have listed here with the one that I have on the real machine that I'm testing on the real target. So then I go into segments, rebase program, and then I have to remove this and then set it as hexadecimal. And then this base address, I'm gonna set the image base to this address. And then because I already have, I forgot to mention, but I already loaded the driver that I'm debugging in IDA, right?
The vulnerable driver, the one that we are debugging now.
Yeah, exactly. So if I click OK, you see all the addresses have changed and they are using the same base address now.
Yeah.
So now, if I want to look for something interesting, or if I want to set a breakpoint somewhere, let's say I was debugging this RTL memory copy memory here. So if I want to go here, you see it's not going because the address that I have is old. So I should rerun the script. The Python script is now it's gonna
and check for the new one.
Yeah, it's gonna check for the new addresses. And now if I click on the addresses that are pointing to those functions, then it will take me there. So these ones are references, yeah, to RTL copy here, yeah, and it's taking me there. And if I want to know, for example, here I already found it. This is one of the IOCTL calls, and this is the IOCTL that is vulnerable. This case is this is the IOCTL that I'm gonna use. So this is the driver, and then it's just doing a case for each IOCTL. And then on this one is gonna, if it ends up going into this one, it's gonna run this code. So, and this code you can see already that it's using RTL copy memory. That is basically a mem move. It's moving memory from one place to the other, but in this case is not controlling how much memory, and how and the destination either. So it's not controlling anything here. It's just doing it. It's just moving whatever I gave to this IOCTL from the buffer, and then it's moving it to somewhere, right?
So that's what the driver originally does.
Yes, exactly.
Okay.
But it's not controlling, it's not protecting how much memory is going through this, and then that allows me to take control of the flow of the program.
Yeah.
All right, so here what I can show you is that we could do it with IOCTL++ to replicate that. But let's first set a breakpoint on RTL copy memory. So for that, because now we have the address, and this is a nice trick if you are doing pseudocode on IDA or Java. I think Java does it by default, but in IDA you have to synchronize the views. So you can say synchronize views IDA with IDA with this view, and if you want to have it just like in Java, then you can do something like this. So every time these two are now synchronized, so if I'm reading the code in C++ here, and I say, okay, but I would like to set a breakpoint here on this condition. Then as soon as I click it, it will synchronize it on the assembly part. So if I want to set a breakpoint on RTL copy memory, then I click on it, and then it will not only show me the call to RTL copy memory, but also is gonna highlight. That's quite interesting and quite important, because then you don't have to go to MSDN, right?
Exactly.
Because you already know MSDN is basically the manual for that you should check. Let me show you RTL copy memory.
That's actually a nice trick.
Exactly. And then here you can see that is having destination, source, and length. And that's how it works. But the disassembly of it, I go back to IDA, you see that is the destination, source, and is also giving you the length here, and here's destination, and basically he is setting up between R8, EIX, and RCX. Move, this is of course move, and then LIA is load specific address. And if another trick, I already have it, is to set the auto comments. Then IDA will add these comments for you. But here you will see, if you are debugging it, then you shouldn't put a breakpoint here on the code itself. If you want to actually debug RTL copy memory, what you should do is to set a breakpoint here when it starts. So you can also check the values and what happens when on these values, right, that you are setting up as arguments. So if we want to set a breakpoint, then we have to copy this from IDA, because remember we already set the base address.
Yeah.
Then we go back into WinDBG, and then we can set a breakpoint 0x, and I'll be adding the 0x so it will understand that is hexadecimal, same with IDA. And now on the lower side of the screen, if I click on breakpoints, then we'll see that I have a software breakpoint set here.
Yeah.
And the base address of the running kernel matches the base the addresses that I have on this debugger, static debugger.
Good.
All right, so now I can continue. I can click on go, and now the machine should be running, and then I can trigger. I could trigger the IOCTL using IOCTL++, but I already have an exploit for it.
Okay.
I'm just gonna show you the breakpoint and how it works.
Have you written that exploit yourself?
It is based on a different exploit. It is based
Mm-hmm.
on a different exploit, but the whole part I wrote it myself.
Okay.
So let me check here. So here's the exploit, and here's the IOCTL call. If we wanted, we could set it here, and then in IOCTL++, we could set the driver that we wanted to use. We could search for it. It should be HER, this one, and then we can set like that, and then the IOCTL that we wanted to use should be, we had it in IDA as well, but we can also take it from here. We already have it.
Yeah.
So there you go. That's correct. Okay, and now the input size, you also have to get it from the IOCTL call. I know it should be 8. And then you can type here whatever you wanted, because this is what we're gonna be sending. Is just a bunch of fields. But instead of doing that, we can also do it with the exploit. That is basically doing the same, but using a C++ program.
Mm-hmm.
So now, as soon as we execute it, then we are gonna hit the breakpoint. So it says breakpoint 0. This is our breakpoint has been hit. And now, if you remember from IDA, we are here, move R8 EAX.
Yeah.
And here we are, move R8 EAX. And if you want to know the registers values, we can type R. They will give us the register values. If we want to, for example, check what is inside EAX, we can do that. There is nothing. Well, it might be something, but if we can use the buttons here to step out, step into, step over. We're gonna step in the call, but we're gonna step over this movement. So we can type P to step over, or step here, step over.
Yeah.
Now it's gonna do load a specific address, this into RCX. That this is gonna contain, of course, the load of the buffer that we sent. So actually, if we look at the values of RCX after we execute this, now we are here, but now we can look at the values of RCX. And you see that it contains what we
The
sent.
values.
Yeah. Exactly. And then here we can step into, and then if we step into, it will go into RTL copy memory. But it's not showing me RTL copy memory because I don't have the symbols. But otherwise, you could see RTL copy memory, the name, but now I'm seeing an offset. Yeah?
Yeah.
So if I step into, then I'm inside memcopy. You see?
Oh, yeah.
It has resolved that offset into memcopy, and now we are inside NT memcopy. So we are inside the kernel function. So now we are not anymore inside this .text function from the driver. We are inside the native kernel, inside memcopy function. So this is what we are running. And now it's moving the values from RCX to ROX. And then we can see those. And always, if this is something useful, if you want to look at the backtrace, you can type KB. It will come with KB with the bar. It's gonna give you the backtrace, and then this is gonna give you the return address. You can see if you have overwritten something, and you see that it has pushed memcopy into it, and then we also have the return addresses for this. You can also look at the stack, because this is on the stack. You can also look at the stack here. That's quite useful. So now we're gonna continue. Can continue on it. There you go. And now, well, I already passed through it, but a fatal error has occurred here because we were overwriting stuff that we shouldn't be.
Because of the A's that you have written, yeah.
Exactly. So now the kernel has back-checked, and and it has stopped execution. So if you want to trace it deeper, you have to, of course, look at what are the return addresses, what are the status of the read, and how and actually you can see here that inside the dispatch exception there were a bunch of A's, but for some reason this has stopped executing. And if you want, you can continue it. And then what's going to happen is after the back check, you can get an analysis of it. So now he has back checked. Now it's doing this. It's doing the blue screen, and you can look at the analysis of it. Long story short, we have overwritten a security cookie. That security cookie didn't match with what it was checking. So either you write a little bit. So you want to bypass the security cookie, you have to just leave the security cookie as it is, or read the value using a memory leak of that security cookie, and then put the value back before it's checked, or just try to not touch that security cookie. That's a way. It's not a bypass. It's just preventing that from happening. So basically, that's how it works with WinDBG and the debugger. So now I hope you have a little bit more understanding on how this process works.
Yes, you were very busy with all this research, right?
Yes, indeed. Yes, indeed. And there are more exploits coming, and there are some. I found some things quite scary.
Interesting,
and interesting, and all the development that I'm trying to publish is for older versions or Windows 10 versions, something that can be fixed or is already fixed. But if you want to learn more and go deeper, and if you want to look at what's new on Windows 11 on all these new techniques used on Windows 11 from my exploits, then you can go into Exploit Pack, and then you can access those exploits. If you go to exploitpack.com, the project that you have to get, the tool that you have to get to access these exploits is Exploit Pack, not Control Pack or Kernel Pack, and the tools that I'm using and the code as well. So it's not only for you to execute it and launch it, but it's also for you to learn if you are interested in the topic, of course. If you are interested in learning about Windows kernel exploitation and exploits in general, it's not only for Windows kernel exploits. In exploits in general, then you can, if you get access to this, then you get access to the code as well. And also, we have a Discord channel to talk over exploit development. So look at in your website and exploitpack.com. The Discord channel, and then after you join, go into the exploit development channel, and there you can go free with your questions, or if you have something cool to share.
Great.
All right.
Thank you so much.
Okay, thanks, Mara. And
it was very interesting. It's a lot, but we have a lot more videos to come on this topic.
I know this topic is a lot, but if you are interested in the topic, I can recommend you to go look at kernel programming, the kernel programming book. You can choose find it in Amazon and also from the same authors, Windows and Internals Part 1 and Part 2. Those will get you started.
Yes.
And of course, on our website, look at our blog spots, and also the Explain Pack tool.
Yes, we will be adding a lot more too.
Yes,
Blog
indeed.
posts.
All right, I think that should be it. Thanks, guys, and see you in the next one.
Thank
Bye-bye.
you. See you.
Bye.
Bye-bye.